So I once again request Professor Bhasin to please have the second talk started. Professor Bhasin, please.
Professor Hussain, you are muted. Please unmute.
He has been recently the head of the department, as we already know, and it is during his time that we had a meeting, condolence meeting of Professor Mitra during this for the last time, and he had really organized it very nicely for a very large meeting. I had really rarely seen this type of meeting which was there for some time. So thank you very much, Brajesh Choudhary. He has been really going. He has been abroad for a number of years. Actually, he has spent many years in for Fermi Lab and also in Berkeley. I had the opportunity to have his hospitality at the Fermi Lab for a few weeks when I visited there. I therefore invite Brajesh Choudhary to give the contributions of India's contributions to the CERN and LHC and CMS experiments. Thank you, Brajesh Choudhary.
Good morning, and thank you for the introduction. It's my pleasure to talk at Professor N. Mitra Fest. I was not a student of Professor Mitra as many had been, because I was not a student of Delhi University till MSc. But I came to know Professor N. Mitra when I was a PhD student with Professor R.K. Shupuri, and later when I joined here as a professor in 2004. And I met Professor Mitra several times. He passed away in 2022. I had the opportunity to hold the condolence meeting as well as a lecture in his honor. So this is, you have seen these pictures. I got it during the lectures that I had held in 2023. So this is my tribute to Professor N. Mitra. This reminds you of the inaugural memorial lecture that we had held on Professor N. Mitra's life and time, and it was given by Professor N. Panchapakeshan. So I come to LHC now, and what I'm showing here is an aerial view of CERN LHC, 27 kilometer of circumference. LHC is a proton-proton, proton-ion, and ion-ion collision collider. It has a circumference of 27 kilometers, and there are 4 experiments on it. They are called Atlas, CMS, Alice, and LHCb. And India collaborates in 2 of them, CMS, compact muon solenoid, and Alice, which is a heavy ion experiment. So CMS collaboration, and I would like to emphasize that some of these slides may not be very recent, maybe a year old or so. So take it like that. So CMS collaboration is about 260 institutions from 57 countries with about 6,000 members, but about 2,000 PhD physicists, of which 1,400 pays MNO, maintenance and operation costs. That means they are actively involved into it, about 1,100 PhD students and then engineers and others. India has only 31 PhD physicists, and the number of students from India at any time varies between 60 to 75. So I'm not going to tell this august crowd about how our universe works, but I will just like to remind that our universe is 14 billion years old. And when we are working at 14 TeV center of mass energy, we are going to the first 10 to minus 12, 10 to minus 13 second after the Big Bang, which is somewhere in the electroweak transition region, supersymmetry breaking region. And that's how we try to find about the quarks and the gluons and the forces that act between them and the vector bosons. So what is our universe made up of? We know that our universe is made up of 69% dark energy, 26% dark matter. So we know our universe is expanding. And that's what we call the negative pressure we call as dark energy. It's roughly 69 to 70%. But as all of you follow literature, I do also, and I'm not an expert on dark energy, there are various models of dark energy are coming that whether the rate of increase of dark energy is slowing down or what is happening. And there are better experts in the audience to tell about it. Dark matter, we know that there are matter which doesn't interact either with a strong interaction or electromagnetic interaction, but we see them through the gravitational pull, and they are the dark matter. So what I'm going to talk about is roughly 5% of the universe. And what we are interested in from the time of atom to the quarks and gluons. And again, I'm not going to go through this slide for this August audience. So we know about the fundamental particles and forces, 6 matter particles or 6 quarks, up, down, charm, strange, top, and beauty, and 6 leptons, electron, muon, and tau, and 3 neutrinos, nu e, nu mu, and nu tau. And the force particle for the electromagnetic force, photon, the strong force, the 8 gluons, for the weak force, W plus W minus, and Z. And now that the Higgs has been discovered, most of these particles, except for the neutrinos, interact with the Higgs field and they attain their masses. So the status of particle physics today. The status of particle physics is that the standard model is well understood very much. We do not know anything beyond this standard model, but then there are evidences of new physics which we are unable to explain very well. One is the accelerating universe, that is the dark energy. Second is the missing mass, that's the dark matter. Third, that we know that neutrino has masses and they mix. That means as they travel from one place to another at a certain distance, the mass eigenstate changes and the mix of mass eigenstate changes and they become, it is the flavor eigenstate, different flavor eigenstate appears. So we do understand that there are physics beyond the standard model. So some open questions in particle physics, which is interesting. And this came through the P5 report of the American High Energy Physics about 10 or more years ago, but it is still valid. What is the nature of dark energy, which constitutes 3/4 of the universe? What is dark matter and how one can find it? How did the universe begin? Then in the intensity sector, what are the masses and properties of neutrinos? What role did they play in the evolution of the universe? How are they connected to matter-antimatter asymmetry? Are elementary particles fundamental? And I have personally worked on quark substructure like Q star, B star, and others. How do these particles acquire mass? We know that Higgs boson, we have found the Higgs boson, and we know the answer that these fundamental particles, except for neutrino, interact with the Higgs field and they get their mass. But do we have only one Higgs boson or multiple Higgs boson? And we are still looking into it. What is the physics beyond this standard model? What are the new particles and forces? Do all forces of nature become one at some energy scale? And we know about the unification of the electroweak force, but does at some energy scale electroweak and a strong force also unite? We have no idea about it. Why there is matter-antimatter anomaly in the universe? What led to it? Obviously, when Big Bang happened, there was the matter-antimatter parity, as the basic physics will say. So what happens to all the antimatter? And as we know, with the experiments in the space, we haven't been able to find much antimatter even in space. So what happened to the antimatter? And are there only 3 generations of particles? So these are all fundamental questions that none of the that experiments have answered till now. So energy frontier, this is the tunnel of the Large Hadron Collider. And what I'm showing here is basically the dipole magnet, one of the dipole magnets. So LHC, Large Hadron Collider at CERN, is the biggest and most powerful microscope in the history of mankind. It probes the shortest distance, somewhere between 10 to minus 18 to 10 to minus 19 meter. It has been in operation since 2010. Higgs boson was found in 2012. A Nobel Prize was given to the propounders of Higgs boson in 2013. And hopefully further discoveries may come. So I'm not going to go again through this slide for this crowd. As you see, one TeV proton, which was at Fermilab. That's why the accelerator at Fermilab was called Tevatron. It was able to resolve distance of 10 to minus 18 meter according to Louis de Bruuy's equation. And 7 TeV proton is somewhere between 10 to minus 18 to 10 to minus 19 meters, the shortest distance yet seen in the universe. So LHC, as I said, is a proton-proton, proton-ion, and ion-ion collider, 27 kilometer in circumference, 100 meters underground, 4 experiments. The accelerator ring has about 9,300 dipoles, quadrupoles, sextupoles, and octupoles. Dipoles are the magnet which bend the beam, moving almost with the velocity of light. Quadrupoles are the magnet which focuses the beam. Sextupoles and octupoles are the magnet which correct the various deformations when the beams are moving. The magnets are pre-cooled to liquid nitrogen, roughly 80 degree Kelvin. Okay, it's 77 degree Kelvin, using 10,000 tons of liquid nitrogen. And they are further cooled. The magnets are cooled to 1.9 degree using 60 tons of liquid helium. Construction time was roughly 10 years. There are 2 experiments, CMS and ALICE, on which about 20 institutions, each from India, are involved. So CERN accelerator, it is not one accelerator through which we go. It is 5 accelerators. First, it is a linear accelerator, number 1, which accelerates the proton up to 50 MeV. Then we get the booster, number 2, which accelerates the proton up to 1.4 GeV. Then number 3, proton synchrotron, or PS, which accelerates the proton to 25 GeV. And then the 4th is superproton synchrotron, number 4, which accelerates the proton to 450 GeV, which feeds into Large Hadron Collider, which is number 5, and it accelerates the proton to 7 TeV. So 2 protons, if I was saying electron, my apology, 2 protons of 7 TeV each collide head-on at different experiments. So on the left side, the picture is of a dipole. It is 1230 of these 8.3 Tesla magnetic field dipole, which bend the beam around the ring, and they each weigh 28 kg. On the right, the picture is of the quadrupole, which I took personally, and you can see how the quadrupole looks. It is an old picture from 18 years ago. This is how, from the tunnel, the detector looks as I had taken the picture myself. Now, India's contributions to the Large Hadron Collider. I know people know the physics here, but everyone may not be familiar with all the contributions that India has made to the Large Hadron Collider over the last 30 years, and it is substantial. So India participated in LHC construction and commissioning, which was the cooperation agreement signed in 91, but India became more active, as you know, in a little later. And most of the contribution was in kind. Hardware contribution for construction of Large Hadron Collider, commissioning and recommissioning, and software development. Then India also participated in novel technology for accelerator project, NAT protocol, in which it made hardware combination, vacuum chambers, dipole magnets, and optics design and commissioning of the accelerator and control software. And then they are still working on LINAC 4, which has been finished for the superconducting proton LINAC. So what did India contribute? And I will read the top part of it. It gave liquid nitrogen tanks, 50,000 liter capacity, 2 of them. It gave superconducting corrector magnets, sextupole, decapoles, and octupoles, 1146, and 616. It gave 7,000 precision positioning jack on which the accelerator of Large Hadron Collider stands. It provided 5,500 quench heater power supplies. It provided racks 6,200. Control electronics for circuit breaker of energy extraction system 70. Local protection unit 1,400. Superconducting dipole magnet measurement expert support 100 man-years. And then you can look through the slide. Here are the major contributions to the LHC. So superconducting corrector magnet on the left-hand side, it is from KECL Bangalore. Quench heater power supply from, again, ECIL Bangalore, 5,500 of them. Local protection unit from ECIL Hyderabad, again, 1,435. On the bottom left, precision magnet, about 7,000 made in Bangalore and Indore, on which the accelerator stands. And support for LHC hardware commissioning about 18 man-years. So main physics goals of the LHC experiments are test the standard model with very high precision, search for the origin of mass through the discovery of Higgs boson. Hopefully the same Higgs discovered, searching for other Higgs do if they exist. Search for dark matter candidates through the discovery of lighter supersymmetric particles, physics beyond the standard model, and understanding of the further 26% of the universe. Understand the nature of a space-time and unification of forces through search for extra dimensions and micro black holes. So we know that if extra dimensions exist, okay, we might be able to produce micro black holes which will have a certain signature in the detector. Also, there are extra dimensions model like Random Sundaram and other models which predict certain signature, but we haven't found them. Study matter-antimatter asymmetry to shed light on the origin of universe. Yes, LHCb has recently measured a certain asymmetry, but that asymmetry is not good enough to explain the asymmetry in the universe. Understand the nature of Big Bang or primordial plasma to go back to the beginning of the universe. All these goals of the LHC are covered by the CMS experiment. And I would like to stress here that by now we have graduated about 120 PhD students. And the Indian groups has covered the full spectrum of physics analysis, from standard model physics, QCD, electroweak physics, top physics, Higgs physics, discovery of Higgs boson, TTH, Higgs pair production, to BSM physics like substructure of the physics or supersymmetry. We have explored all of them. So towards the high luminosity goal, we are in 1925. We are going to take run this year. Then there will be 3 years of shutdown. We will start again 2030, and then it will go for a long time. So India is involved in the detector upgrade, and now I'm going to come to that. So this is the compact muon solenoid detector. All of you must have seen. Inside is the tracker in the purple. In the green is the silicon tracker. Okay, it's made of silicon wafers. Then we have the lead tungstate crystal in the green color. Then in the blue color, we have the hadron calorimeter, which is made of scintillator and steel. Then we have the yellow and red part. The red part, before that, let me say there is this 3.8 Tesla magnet in white, which provides the magnetic field to all the charged particles that are coming out of the vertex. And then in the yellow and red, yellow are the muon system, and red is basically the steel substructure for the muon system, which also provides the magnetic field. I will skip this detector. So particle identification, as you know, that we look at the photon and electron in the electromagnetic calorimeter, pi plus, pi minus, neutrons and others into hadron calorimeter, and muon is the long particle that is curling out. So India's main contributions to the CMS detector. India started with outer hadron calorimeter, which is made up of scintillator and steel, and it measures jets and missing energy. Why it is so important? Because if you don't measure the jets and missing energy very well, you will not be able to measure the beyond a standard model physics very well. India also started with pre-SAVR, which is on the left-hand side on the slide. What was pre-SAVR? Pre-SAVR was made of silicon wafers and lead plate. What it did, that it converted the pi zero into 2 photons, and the SAVR from 2 photons will be very different from 1 photon. That was very helpful in disentangling pi zero, which is a background to the photon, and that thus the pi zero becomes a background for Higgs to gamma gamma search. So these were in the initial phase. Then India put about a couple hundred muon RPC detectors. In the present phase of upgrade, India is already upgrading the muon measurement system with the gas electron multiplier for the high luminosity large hadron calorimeter. India is also making silicon outer tracker, which will be used for charge particle tracking, pileup mitigation. India is also upgrading hadron calorimeter with electronics, which measures jets, missing energy, and lepton ID. And India is involved into EdgeCal with certain electronics. So this shows you silicon pre-SAVR detector made by Delhi and BARC. We supplied about 2,000 modules. BEL Bangalore supplied it. Our students went there and they did the work there. I personally visited there, and it was about 50% of the total pre-SAVR that was supplied to CERN. Outer hadron calorimeter was done by Punjab University and TIFR, and this shows you in the picture on the right-hand side, the red region where it covers the detector where the thickness was less. Then the resistive plate chambers, it has good position resolution with fast timing and signal collection, robust and highly efficient in triggering on muons in a busy environment. We provided 50 RPCs, high voltage, low voltage power supply. RPC was also developed by India-Alice collaboration. RPC can be used in medical imaging, tomography, and port security too. And you can see the pictures here of Delhi University and Punjab University. GEM detectors, you can see Delhi University and Punjab University. It is from the Delhi University picture. And on the right side, you can see the 3 GEM detectors with all of us. And 17 GEM detectors has already been delivered for the run 2. And we have worked in close collaboration with Micropack for large area GEM foil development for the next phase. And GEM can also be used for X-ray imaging. This photo, I'm showing you that how GEM detector can be used for X-ray imaging. On the right-hand side, you see some keys and metal objects are put there, and then X-ray is passed over them, and GEM detector is on top and bottom of them, and you see their image. And what we do that after doing the analysis, here you see the mass thickness versus the hit density. So you can look at the objects while it passes through port security, that what kind of object, of what density object are going. And it is possible to use GEM detector for neutron imaging. So this is the power of, this is the proof that has been published, but it has still to be industrialized. Various other detectors are being done. And here I can show you that the rate will be very high. On the top left, 140 collisions. In the middle, sensor qualification center from the tracker for Delhi University. Aluminum carbon fiber stiffener produced at IIT Madras. Bottom left, hexaboard designed by Science Institute of Nuclear Physics, fabricated in industry. In between, indigenous fabrication of sensor and wire bonding, TIFR. And for the trigger system on the right, fabrication of high-speed FPGA board by TIFR. This has also given at grid computing at VECC and TIFR, and this is just a statistics for some period of time, but this has helped the computing system in the country. NKN technology came because of this, and as you can see, NKN technology has connected the institutions in India. How much time I have? Hello? Hello?
I believe you have about a minute. Actually,
Okay.
I would have probably considered that to be less than a minute, because you are hoping to also have a QA session.
Okay, fine. So few snapshots on physics. I am not going to go through the details, but these are the production and decay diagrams of the Higgs boson, gluon fusion, vector boson fusion for the production, and the Higgs boson with vector boson production and TTH production. So what I would like to emphasize, because Higgs boson is the most known physics from the LHC, Indian groups has contributed in all facets of Higgs discovery. Here, the two diagrams shows you Higgs discovery in gamma gamma and Higgs discovery in ZZ is star going to 2 electron and 2 muon. Higgs boson was discovered. You have seen all these pictures. I'm not going to go through it. We have measured the Higgs mass to a very high precision. We have also measured the Higgs width, the Higgs coupling with various Higgs production and decay coupling with in the various modes. And you see that it agrees with the standard model, and it was published in Nature. We have looked at Higgs coupling to fermions and vector bosons, and you see that our latest result on the top in the left picture is the black cross is around 1. And then you can see that with the various particle which decays into the Higgs boson, which decays into various particles or couples to them, you see that they are coupling as a function of mass on the x-axis. Y-axis is the coupling fermion directly, and with the vector boson with the square root, it is on a straight line, so it fits very well. I'm not going to go into the future. Indian industries which partner towards CERN collaboration, it's a very long list. So Indian industry is heavily involved. This is the picture of Nataraj at CERN. Most of you have seen it. Professor Kakodkar, Dr. Kakodkar is in the background. That's the then CERN Director General and perhaps the Ambassador of India. Then you can see there is this outside the CERN called globes. Here it's written Madhav Shankara Anant Sreni Bhaskaracharya Dutya Nakshatra Bas ki lambai का माप 365.258 दिन Brahmagupta Sunya and Rin Sankhya. So India's achievements are everywhere. Indians are doing well. This is my enlightenment in CERN itself. And very recently, 2025 Breakthrough Prize has been given in fundamental physics to ALICE, Atlas, CMS, and LHCb, about 7,000 people or 13,000 people. There is a large number, but it tells you that the physics has been further recognized and India is contributing. So summary is India's contribution to CERN LSC program has been substantial. Indian physicist has contributed to every aspect of detector, software, maintenance, and operation to physics analysis from QCD, electroweak, top Higgs, BSM, dark matter, compositeness, SUSY to TTH and HH, Higgs coupling, self-coupling physics to heavy ion physics. We pay about 2.5% of MNO for CMS and are involved in about 8 to 10% of publications. We are doing very well. So thank you to all of you. Thank you to taxpayers of India, DAE, DST, and CERN for providing such rich opportunities, we are very thankful. I'm done. Thank you.
Professor Bhasin, perhaps if you deem it fit, we could have maybe one question or so. Professor Bhasin, can you hear me? Perhaps he might be otherwise engaged.
Haridas has a hand up.
Oh yeah, please go ahead, Professor Haridas.
Thank you for a wonderful talk. I was just curious that there's a lot of talk about the so-called Wakefield acceleration, which the proponents say will bring down the accelerator size by as much as 1,000. I was just wondering what your take on that topic is.
Okay, so first, I'm definitely not an expert on accelerator physics and Wakefield accelerator, but I have followed it to some extent. And Wakefield accelerator R&D was going on at Fermilab, and they have made some thing, where you can accelerate to a certain energy, but Wakefield accelerator on a larger scale where you can accelerate a particle like proton or electron to very high energy, let's say within hundreds of meters, is still, I will say, a dream.
Thank you.
I think with the permission of the chair, since we are about 5 minutes behind schedule, let us thank again Professor Bhasin for his chairing of the session, and Professor and the speakers of the session that he chaired, Professor Indraneel and Professor Brajesh Choudhary.